All right, so I'm going to talk a little bit about the project that me and Kev put together about admissions modeling. And it was for modeling and to predict potential students attending or not attending Augustana. So a little bit of background. The data was given to us by the Office of Admissions. It was collected by a series of surveys in 2010 about those applicants. And the data set was built, there was like around 2,000 plus data points for us. And some of the variables they provided us were, the categorical ones were state, gender, per ethnic, which is Hispanic, non-Hispanic, race 1, which is Caucasian, African American, Asian, race 2, which is the second race if they put that, major 1, which they desired to major in, major 2, major 3, and then the numerical was ACT, SAT, class percentage, the class size, the status of whether they're coming or not. That's actually a categorical. The AP rating and the DEM int. The AP rating is a score given to the student from the school, and then the DEM int is the interest demonstrated by the student to come to Augustana. So the model we chose was a logistic regression model to model this data, and we divided into training and test data sets, which I'll talk about in a minute. And the key point we're going to use in analysis of this model is the AUC value, which is helped us determine the model, which is the area under the curve, which I also cover further. And for the actual analysis, we used R programming. So the goal is to determine the most optimal predictors to model applicants' attendance to Augustana with our dependent variable status. So that categorical variable status is what we will determine to use, or to use to determine whether a potential student is coming to Augustana or not. And that's our Y variable, would you say. Some of the assumptions, these are just a few of them. There's more in the report, but one was the individuals answered honestly on their survey. One of the things we had to do was insert blank data, and for blank data we needed default values, and then also we used random data points for our test and training data sets. So going on, what we started with was a process of cleaning the data. The first was to eliminate the columns that we wouldn't need. And you can see here in the A1 corresponds with 1A here, or A1 or 1A corresponds with 1A here, which is what we used to eliminate the columns that we did not need. A few of them was major 2 and 3, race 2. We determined those just by examining the data that. And they all, and SAT was also another one that we dropped. And it was just because there was so many blank data in there, and we didn't feel like trying to convert or default those values as well. The next step was inserting modes into the blank data for the categorical. First, we had to put NA in there, and then insert the mode. And 1B is corresponding with that, and that's an example with the race 1, inserting the mode. And then we inserted means and medians for the NA numerical data. The example over there is AP rating, that's the mean. We only did one with the median, which was size, because it was kind of an unbounded, and if you have a bunch of schools with class size of 200, and then a 500 class size gets in there, it can bring the mean up, so we decided median. And then we went on to convert the categorical data to binary categorical, which we used the levels command. We did that with gender, status, also gender status, major one, and state. And we did in-state and out-of-state, which was based on Illinois. The next step was dividing our data into test and training data. We used the seed, which allowed us to use the same random data set every time. And the way we divided it was 60% training data and 40% testing data. Going on, the next step in our process was building the actual models. The first one we built was a non-interaction model with the logistical GLM function, which you can see is right here with all the different predictors in there with no interactions between them. And the next step was doing variable selection on the non-interaction terms, or on the non-interaction terms. And based on the p-values reducing the AIC, it would eliminate variables from our model to give us the most optimal model based on those predictors that we gave. And then what we did was for our test model, we used the training model that was built from the training data because the test is used for that validation in the future. And then after that, we built our interaction model. After that, we took the results of the variable selection in the non-interaction model and built our interaction model based on those predictors and the interaction between only numerical and categorical, because you cannot do categorical. Then we also did the variable selection on the model again, and it produced this result here. And we can see that the AIC went down. This is what it started as, and this is what it went down to. So this is the model that it gave us. And then again, for the interaction test, we used the interaction training model. And then for the model analysis, the next step we did is built the ROC curves. The ROC curves for both test and training for the interaction and non-interaction models that we built. And then after that, we ran the performance on it to see the AUC, or the area under the curve, under that ROC curve, which I'll cover more later. And then we determined the accuracy of it based on the confusion matrix, and also determined the cutoff to raise that accuracy of the model. So as a result, me and Kev picked this model and these predictors as our most optimal model. And you can see all the coefficients correlating to each different predictor. Obviously, I'm not going to go through all of them, but one of the things is we determine these as by p-values, and the p-values represents the significance of, or not the significant, but shows the test statistic on that predictor and whether or not they're able to stay within the model. Now we also talked about having some, our cutoff was 0.05, what we talked about, and what the step function did is it still kept some with a p-value above 0.05, but it also lowered the AIC enough to allow us to keep it. So this is the model we went with. And interpreting the coefficients for the categorical variable, obviously, we chose state 1 for this, and the coefficient is obviously 0.1 or 0.819495, which is in log odds. And so we converted that to odds by raising it to the exponential. We also did the probability, which is the odds over 1 plus the odds. In a way, just a verbal interpretation is if you hold all the other variables constant, a potential student from Illinois has the odds of 2.26935 to 1 of going to Augustana. And then the numerical variable interpretation is coefficient is obviously that up there. And we convert it again to odds and also probability. And then another verbal interpretation is the potential student increases their odds by our odds value as the ACT score increases. And so when we determined our model, part of the reason why we determined our model was the resulting ROC curves in the area under the curve. The resulting ROC curves are, as you can see up here, this is the non-interaction and this is the interaction. And it's based off the sensitivity and 1 minus specificity, which is part of the confusion matrix that I'll cover in a second. But this is a visual interpretation of what our model is predicting and showing how well our model is doing. A perfect model would be on this scale would be 0, 1, so all the way up to here. So that would be a perfect model. It would have an AUC of 1. So moving on, as a result, in the non-interaction, our AUC was this, and then our non-interaction was this, and our interaction was this. So obviously we went with our interaction model. And this is just showing a visual of the area under the curve that it's calculating, which allows us to determine the best, or the most optimal model from the data that we used in building. And then determining cutoff, we used a confusion matrix, and our cutoff determined was 0.481 based on the confusion matrix with an accuracy of 71.7%. And the way we calculated that was taking this value and this value summed over the entire table or matrix, summed as well for the true positive and the true negative values over the entire value. So going into discussion, some of the strengths that we had is we had a large data set to work with. One of the weaknesses is that we had to fill in blanks with MAs, and obviously we want as much consistent data as we can without having to put in those default values, whether it be mean, median, and mode. Ways to improve our model is repolling students that took the survey to make sure we get all the data that we need, and then also using more years of data, so we have way more data points to look at. This model can be used by the Office of Admissions here at Augustana, based on that they use the same survey. Other schools would have to use, if they wanted to use this interpretation, would have to, or this model would have to use the similar or same survey to collect data. For future research, admissions could collect data over the years, increase predictability, add more predictors, and a few of them, one of them I thought was possibly including scholarship, how much they are getting there, or financial. And as a result of our analysis, we built a model that was 71.7% accurate on determining enrollment in August. Can you hear my